neural networks is a very old topic. Actually, it is not very new. So I'll be covering that in the history today. So it's a very old topic that has been started long back. Okay, but you may notice that these things have become very popular only very recently. Okay, not more than say 10 years. Okay, from 2010 onwards, or maybe or the past 10 years only, these have become very, very popular. And the reason is, one of the reason is the convolutional neural network. Okay, so this convolutional neural network has really challenged, actually has come up very successful in various challenges that has in which it has participated, and it almost gives human level performance. Okay, that's the great thing about the convolutional neural networks. And the last that's good, and this convolutional neural network will be done on day 4, and on the last day, so we will be seeing about the sequence modeling using recurrent neural networks. Sequence modeling is actually a difficult task. So the data comes as a series. Okay, it may be a time series, or it could be a sequence of days or weeks. Okay, or audio or video. So different examples. Okay, the stock market exchange data from the stock market exchange, the weather report, the temperature or the humidity over a period of time. So all these are sequence modeling, and the main difference between a sequence and other type of inputs is, in other types of inputs, one input may not depend on the other input. Okay, say for example, you take the ith input may not depend upon the I minus 1th input, or may not depend on the I plus 1th input. But whereas in sequence modeling, every input x of I, for example, will depend upon the previous inputs. Okay, so there will be correlation between the inputs, and that is why it's called sequence modeling. And then we need a special kind of a mechanism to decode this type of what you call correlations that are hidden inside a sequence, and that can be done using recurrent neural networks. Okay. In fact, as I'll talk in the history part of it, all these are same. All these are actually not latest topic. They are all very old topics. Okay, but they have been made possible. Okay, only recently. Okay, so the reasons are all those things I will be discussing. Okay, so this goes with our agenda for the next 5 days. So the next thing is the history. So it is always better to before you learn a particular topic, to have a look at the history. Okay, so now history is not going to be boring. Actually, it is something like we are going to see have a literature survey. Okay, so you know how this field has developed over a period of time. So that is what actually we mean by history. And the chronological order that I'm going to discuss may not be the same order in which the events have happened actually, but this chronological ordering has been done based on the topics. Okay, how the topics are interrelated, and based on that the chronological ordering has been done. Okay, so long back. Okay, you can go see the bar which is shown below. Okay, so in 1871 to 1873, so it's a very, very long time. So at that time, the neural network, actually how the brain works. Okay, so actually you may be knowing that neural network is actually mimics the function, the way our brain works. Okay, it is actually based on the human neurons. So when it comes to human neurons or the human brain, so in the old times it was almost it was thought that the human brain is not cells, not made up of cells, but whereas it is a gel, something like a gel or a continuum. Okay, single continuous mass. Okay, so the entire brain is a single continuous mass, and so all sorts of decision making or all sorts of communication happens within this blob. Okay, and this was called the reticular theory, proposed by Joseph V. Gerlach. But as days went by, okay, there were improvement in the staining techniques. okay, staining techniques. So that that were carried out by taking pieces of brain tissues, staining with some chemicals and observing them under the microscope, and then they found that Camillo Golgi, he discovered a chemical reaction that allowed him to examine neural tissue in much greater detail than ever before in 1873, where he could see neurons. He could see individual, the brain is not a gel, but whereas it is something made of neurons. And this neurons, other than what they thought is they are not individual, but they are all connected. Okay, now, they are all entangled. I would say entangled means all are connected, and therefore still the reticular theory was valid. Still they thought the brain, entire brain, even though it is made up of neurons, it is all connected, okay, as a single blob. And still Camillo Golgi was the proponent of reticular theory. Then came the Neuron Doctrine. This Neuron Doctrine is actually it is a breakthrough that says that the brain is not a continuum of gel or a single substance, but whereas it is composed of individual cells called neuron. And this was done by Raymond Y. Kegel, who made use of Golgi's technique to using the staining techniques, and he proposed that it actually made up of discrete individual cells forming a network as opposed to a single continuous network. Okay, so he said that the individual cells, neuron cells, are connected, okay, and they form the entire brain. It is not that the entire brain is a lump of mass. It is not like that. That's what he did in 1888. Okay, the Neuron Doctrine was proposed. And then the term neuron was coined by Heinrich Wilhelm Gottfried, okay, in 1891, and he further consolidated the Neuron Doctrine. Okay, but at the same, what happened is during 1888 and 1891, the Nobel Prize for Physiology and Medicine was awarded to both Kegel and Golgi, even though Golgi was actually proponent of the reticular theory, whereas Kegel was proponent of the Neuron Doctrine. But still the Nobel Prize was awarded jointly to both these scientists, okay, even though their belief was different, okay. Because at that time there was no evidence, scientific instrument available to measure or to look into the cells more closely. And both the theories, they found they were what you call gave much tremendous input or contribution, and therefore both Golgi and Kegel were jointly awarded the 1906 Nobel Prize for Medicine. Then came the time, say Nobel Prize was awarded in 1906. In 1950, almost 45 years later, electron microscopy came up, and using this electron microscopy, it was able to find that the neuron cells join with other neurons through something called a synapse. Okay, so that's a junction. Okay, it was discovered because two neurons, they are connected through dendrites. Dendrites are some hair-like structures, and at the point where the hair-like structures join, there's a junction, and that junction is called a synapse. And you can see in the picture that there's a gap between the junctions, and at this gap, what happens is the two neurons communicate through chemicals called neurotransmitters. Okay, so even though the entire neuron is actually electrical, it is basically electrical impulse based, but at the junction there happens to be some chemical transmission. Okay, the junctions are not connected, they are actually apart. There's a gap, and between the gap there's some flow of chemicals, and these chemicals sometimes inhibited the other neuron. Sometimes the chemicals excited the other neuron. So based on this junction, the synapse could be called inhibitory synapse or an excitatory synapse. And later it was found that this synapse is what that gives the learning ability to humans. So the connections are strengthened or the connections are inhibited based on the learning. Okay, so it is not the neuron cells, but it is the connection between the neuron cells that leads to learning. It was found later, but according to history, 1950 only when at that time it was clearly seen that the neuron doctrine. Okay, so the neuron principle was right, reticular theory was wrong. Okay, so the brain indeed consists of individual cells called neurons, and the neurons are connected by synapse. Then came up the field, actually people have started coming in, the logicians. Okay, so these artificial neural networks is actually a subject that is cross-discipline between the neurologists and the logicians. So people are, the logicians are the scientists, computer scientists, who are the people who are actually now are after the search to see how thoughts are actually generated, okay, how the brain works. So this has been a riddle, actually, though nobody could puzzle, or something which nobody could resolve for a long time. So many people are working on that for a long time, and they always wanted to know how this brain works. Okay, so how can we make a model of the brain? Okay, and in this process, the fame, that's what I told you in the beginning itself, that AI is not a new subject. It is a very old subject that started in 18 something. Okay, and it has been so long, but what has happened is there has been lots of ups and downs, undulations. So lots of ups and downs in the AI fame. Okay, sometimes it was many people worked on it, and sometimes many people actually people don't they ignore AI for some time. Then again interest will come up. Some inventions will be there, some discoveries will be there, or some new theories will be proposed, and again people gets interest. Okay, like that, there's going to be ups and downs in the fame of AI. So the first thing that was the neuron model. So when you talk about the actual biological neuron, and you take the McCulloch's Pitt, okay, model. So McCulloch was a neuroscientist, and whereas Pitts was a logician. So both they joined, and they presented a very simplified model of the neuron in 1943. Okay, so it's a long back. And in this, what they did was actually they said the neurons contains, it's a simplified model. So this center part is the artificial neuron, so which gets input from multiple inputs, say x1, x2 up to xn, and each input is a binary input. Okay, it's either 0 or 1, and these inputs are fed in, and this G is an aggregator. This simply adds all the zeros and ones, simply adds them, and this function f will be 1 if G is greater than or greater than 0. Okay, G should be greater than 0, or if G is equal to 0 or less than equal to 0, this because you know the inputs can be 0 or 1 only. Okay, so if all the inputs are 0, then the output will be 0. Otherwise, if any one input is 1, the sum of the aggregate will be done, and you will get 1, and of course the output will be 1. So this is a very, very simplified McCulloch-Pitts neuron, artificial neuron. The problem with this is actually you cannot learn. Okay, so tomorrow's session I will be dealing with that. So for today you can just take it as an introduction. So the problem is that here we cannot learn. Okay, it is all thresholded. Actually, the threshold I have set is 0. Okay, if when you add all x1 plus x2 up to xn, if the threshold is greater than 0, if the sum is greater than 0, where 0 is the threshold, then the output is 1. If the sum is equal to 0, then the output is 0. So it is hard threshold. Okay, you have to fix the threshold. It is okay. So fixing the threshold is done by hand, and there's no learning component in this. Okay, so it is only a very simple model, very, very simple model, McCulloch-Pitts neuron model, And we'll see that you can use this McCulloch-Pitts model to implement logical operations, say AND gate or OR gate, okay, and NOT gate, okay, but not the XOR gate. Okay, so that we'll see in the next tomorrow's class. So some simple binary functions, simple binary functions can be carried out by this McCulloch-Pitts neuron. Following that, Frank Rosenbelt in 1957 to 58, he proposed something called the perceptron. Okay, so the perceptron is again a simplified model like what I have shown before for the McCulloch-Pitts, but here in addition to inputs you also have weights associated with each input. So some inputs are given weights, less weight, some input are given more weight. So say you may ask why you have to give weights. So of course, say for example, say whenever you buy a TV or some mobile phone, a smartphone, we give different weightage for different features. I can say X1, X2, Xn are features of the mobile phone. Say the screen size, say the battery backup, okay, then the different features. So some features. So camera, okay. So what's the resolution of the camera? So you may, some people will give more importance to some features. Say, for example, maybe some people may want high resolution camera, some people may want a touch screen which is very sensitive, or a screen size which is big, okay, like that. So depending upon the different features, some features can be given more emphasis, where some features can be given less importance. So that is what actually the W1, W2, W3. So here, the neuron makes something called an aggregation. It makes an aggregation, okay. So a weighted aggregation, not aggregation of the inputs, but a weighted aggregation. And after that, the threshold, again the threshold is set. And if the weighted aggregation or weighted sum is greater than the threshold, then the output Y is 1, okay. So this is actually called a perceptron because it has the learning ability. Why it's called a perceptron? Because the W1, W2, Wn can be adjusted or learned. Okay, I will show you tomorrow that this again the threshold what comes here in the neuron cell, that can also be learned. So in the previous case McCulloch-Pitts, the threshold has to be set by the user, but here it is not hardwired. It is the threshold can be learned. The weights can be learned, okay. So therefore, there is a learning point. There is a learning ability of the neuron, okay. Just like how we learn over a period of time. So because of that, the perceptron was the first artificial neuron, and you see that long back, say 1957 itself. Say the Frank Rosenbelt, he pronounced that the perceptron may eventually be able to learn, make decisions, and translate languages. See how far-sighted. Okay, say so they could see so much. Say almost a century, so 50 to 60 years advance. He could see that using computers you can do. Say using artificial intelligence or neurons, you can do machine translation. You can make decision support systems. You will be able to learn. Okay, so wide variety of applications, we go for learning, okay. So all those things have been envisioned long back in 1957 to 58. And then New York Times further added by calling the perceptron as the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. See, this is even more envisioning. Say you see, say to reproduce and to be conscious is still not in our. It's still a long way to go. Okay, still we cannot, because artificial neural networks or AI, they still at this point only living things can reproduce and be conscious. But whereas it is expected at that time in 1958 itself that this perceptron will make a big difference, okay, in artificial intelligence. So you see how the people have envisioned the perceptron. So this, I will say, this is the springtime of AI. Okay, so it was the time when many people have started working on that. Okay, right. So from a single perceptron proposed, then multi-layer perceptrons were proposed eventually, where you have input layer, and you don't have a single output layer or single perceptron, but you have multiple layers in between them, and these are called multi-layer perceptron. So why we go for a multi-layer perceptron, that we'll see in detail in the course of our time. But here I would like to say that we go for multi-layer because we want to add some sort of a non-linearity, okay, in our searching. Okay, so everything is in AI is a searching problem. So whenever there is some non-linear functions, okay, so you see all functions cannot be linear functions. So sometimes we need to deal with non-linear functions. In that case, we need to add some non-linearity into our AI or neural. So in that case, we can do that by adding what you call the hidden layers. Okay, so this we will see in detail. Okay, right. So the thing is that the perceptron came, the multi-layer perceptron came. The multi-layer perceptron came during 1965 to 68. Okay. Then, of course, Minsky and Papert, in their famous book on perceptrons, they outlined the limits of what a perceptron can do. Okay, so they said this is what a perceptron can do, and this is this it cannot do. Okay, so it was so what it cannot do. People started thinking. Okay, so that gives you the limitations. Okay, so the limitation of the perceptron. Okay, so since the perceptron had a logic, so the threshold that threshold was actually learned, but still the threshold was a step threshold. Okay, so there was some problem in learning. So that will become clear as we go along, because we'll be talking about gradient descent learning and all those things, in which we always assume that the threshold function should be differentiable function. But actually, when you have a step function, the threshold is a step function, you cannot differentiate. Okay, when you cannot differentiate, you cannot find the gradient, and without knowing the gradient, you cannot learn, because all the learning in the neuron happens through gradient descent approach. Okay, so there was again a breaking point actually. So no, it was a stopping point. At that point, actually, the people now got stuck up, okay, with this problem. And again, what happens? You see that that lead to the winter. So so far it was on the springtime. Now it is the winter time of AI connectionism. So connectionism is actually a branch of AI which deals with neurons. Okay, so where multiple elements or entities are connected. Okay. Apart from that, you have other types of AI, like your expert systems, okay, planning systems and all. So those are actually different, because I would like to say that artificial neural network is again a branch of AI. It is not AI. AI is a bigger umbrella that covers other techniques, but AI connectionism is, deals with the neurons. And this was the time when people actually lost their interest in AI, and it was called the winter of AI connectionism. And this is in 1969 to 1986. So you see almost 16 years. Okay, there was no much development in this field. Then came the some algorithms. Okay, say the people started discovering. Okay, say because the limitations, now they wanted to overcome that limitations. Now they found different functions, thresholding functions. So one function is sigmoid function, I will come later. And another one is the tan H function. Okay, so we'll be looking into them in detail. And the sigmoid and tan H, actually they could be differentiated. And that came the approach called gradient descent approach and the backpropagation learning algorithm. Okay, which was used for learning in case of a multi-layer perceptron. So here you can see a multi-layered neural network. So you have inputs x1, x2, x3, so which are weighted w1, w2, w3, and you see that these are connected to the next level. So what is the sigma represent? The sigma is the sigmoid function I told you. Okay, it's not a step threshold, but it's a sigmoid function. So which could be differentiated, and the output of this sigmoid is applied to the next layer, hidden layer, and the next layer, and this is the output layer. And whenever, because you know that, we will be coming to that, neural network is a supervised learning, and if you know what is the actual y, you know what is the required y or what is the desired y. Now you compute the y and you compare this y and we call it y cap. Y is the desired output and y cap is the actual output. So you take the error, from that error you compute the gradient and you adjust the weight, of the links, and you do that in a backward fashion, and that's called back propagation. Okay. So from the output, find the error, try to minimize the error. When you try to minimize the error, you have to make some adjustment in the weight, previous weight. So like this, the adjustment of the weight runs from top to down, from output to input. Okay. And this was possible only by the back propagation algorithm and the gradient descent approach. Okay. So actually you should know that the algorithm was discovered again, discovered and rediscovered and made for refined this algorithm several times from 60s to 1970s. Okay. It was used in the context of ANN, that is artificial neural networks, by Verbose in 1982. Okay, and it was Rommel Hart who popularized it in 1986. Then some physicists, actually Cauchy, discovered gradient descent in the context of computing the orbit of heavenly bodies. Actually everything is inspired by physical sciences. Okay, some from biology, some from physics. So this gradient descent approach was actually inspired by the procedure or the algorithm that is used to compute the orbit of heavenly bodies. Okay, and that has been applied, okay, into neural networks. And this happened in 1986. Okay. Then people came up with the universal approximation theorem. Okay, so this theorem you should know. Before this theorem, I was talking about some time back about the McCulloch-Pitts neuron, and I told you that McCulloch-Pitts neuron could implement most of the binary logic functions like AND, OR, NOT, okay, NAND, NOR functions. So all these functions could be implemented by McCulloch-Pitts. Okay, but only thing was that the threshold has to be set by the human. Okay, you can create a McCulloch-Pitts neuron that will implement the AND function. Okay, and with that they said that so they came to know that if you have a multi-layer, so I told you again that a single neuron cannot do for XOR and XNOR, but whereas you can have two neurons with a one hidden layer. If you put a hidden layer, automatically what happens is that you can now even implement XOR. So that we will see in detail, okay, later. So the XOR could be implemented by McCulloch-Pitts itself. Okay. So most of the so there was a theorem that said all binary logical functions can be implemented exactly. That's the term I should underline, that all binary functions can be implemented or realized exactly by multi-layer McCulloch-Pitts neuron. Okay, so but after the invention of this perceptron, okay, and the learning algorithms, all those things, it was now stated as a universal approximation theorem that states a multi-layered network of neurons, okay, with a single hidden layer can be used to approximate, not exact. Okay, when you talk about binary functions, they can be done exactly, but any arbitrary function you take, you can the single multi-layered network of neurons with a single hidden layer can be used to approximate any continuous function. It's not binary functions, any continuous function. It could be any function you like, whatever mathematical functions. It should, provided it should be continuous. It should not have discontinuity, because you have to differentiate. Okay, so if a function has discontinuity, you cannot differentiate. You know that. So any continuous function can be approximated by a multi-layered neural network with a single hidden layer. Only one layer is enough. You don't have to go for multiple layers, but that single layer should have sufficient number of neurons. How many number of neurons that layer should have? It should have 2 power n neurons. Okay. So where n is the number of inputs. Okay. So can approximate any continuous function to any desired precision. Okay. So that is called the universal approximation theorem. So here in the diagram you see that, so I have shown you some inputs are there, input layer is there, and this is the hidden layer, and this hidden layer is connected to a single output layer. Now you see here, you see a zigzag wave, and this zigzag wave is actually a arbitrary continuous function, and you see that by adding more and more neurons to this hidden layer, we can approximate this function. We can approximate this continuous function to a desired precision. Only thing is that you have to keep on adding neurons to the hidden layer. Okay, and this theorem is called the universal approximation theorem. Okay, so this was a milestone, and this theorem was pronounced in the year 1989. Okay, it is called the UAT, that is the universal approximation theorem. Then I told you the people lost interest because of some difficulties. Okay, and then suddenly they started revival. Okay, again you see that a revival started happening, the revival of artificial neural networks. Okay, so here again I would like to take one digression, and the digression is that here we are talking about only one layer of hidden layer of sufficient number of neurons, but you can add more layers. Okay, but you can add more layers. But the problem what happened was, when you add more layers, so I'll show you the previous diagram. Yeah, so here you see there are two layers, two hidden layers, and so this is input layer, this one, and this is hidden. The one shown in purple is hidden, green is output layer. So here we have two layers, hidden layer. But what happens is, sometimes there was another problem that was faced when you have multiple layers of neurons in a multi-layer network. When you are propagating the gradient, the error gradient backward in the backpropagation learning, so what happens was, sometimes the gradients vanished, became zero, and sometimes the gradients exploded or saturated. So in both the case, what happens is, whenever the gradients become zero or vanish, or whenever the gradients explode or saturate, the learning stops. Okay, the learning continues only when there is a gradient can change. Okay, if the gradients cannot change, then what happens is the learning is stopped. So that's the problem. So there was, when you add more layers, when you add more and more layers to a neural network, what the people came up with a lot of problem, and that problem was this problem of vanishing gradient. Okay, vanishing and exploding gradient. That was another problem, and because of that, the research was actually, the research in neural networks was went into a what you call winter. I mean when the people did not work because they lost interest in that area. Okay. But what happened was, in 2006, okay, this is the time when again artificial neural networks were revived. Okay, so you see that there is again up and down. Okay, now it has started coming up. So this is the period when I tell you that 2006 onwards, people started applying neural networks suddenly to all sorts of applications, and of course they have been their patronage by huge companies like Google or Facebook. Now you see, anybody, if you take AWS or any company, any big multinationals, they have machine learning, they have deep neural networks library. Okay, the reason is that because of certain seminal improvements or achievements or discoveries that were made, okay, after 2006. So one thing is called the unsupervised pre-training by Hinton and his colleague. That what is unsupervised pre-training? Okay, say, so this is actually something about data compression. This will come in detail in our course. But what do you mean by unsupervised pre-training is, say one of the function neural networks also provides is called a autoencoder. Say autoencoder. So what is an autoencoder? Autoencoder means, say for example, I have an image that is say 100 cross 100 with 3 colors. Okay, so 100 cross 100 is 10,000, 10,000 into 3 is 30,000. So 30,000 pixel values. But this image can be represented by less number of bits. Okay, that's called encoding. So the less number of bits is actually, say I can represent them using, say only 100 bits, 100 neurons. So I will have a hidden layer that has only 100 neurons. The input, which is actually 30,000 inputs, is actually compressed into a layer that is contains only 100 neurons. And from this 100 neurons, I can regenerate my original image. Okay, that is decoding. So that's why I call them auto-encoding. Okay, it's auto-encoders. So that was found, and this unsupervised pre-training was actually breakthrough in circumventing or overcoming the problem of this vanishing and exploding gradients. Okay, so people came to know how to condition your weights such that we don't face this problem of vanishing or exploding gradients. Okay, so that is one thing that is based on autoencoder. Okay, so that we will see, and this was done in 2006. And then more insights into the effectiveness of this unsupervised pre-training. Several people worked on it from 2007 to 2009, and the problem of vanishing gradients and exploding gradients was overcome. Then in 2009, handwriting recognition in Arabic was done successfully by Graves et al. In 2009. So that was the first time when the people applied multi-layer neural network, okay, multi-layer neural network to handwritten character recognition, okay. And this was done successfully by, say, I don't remember actually what was the accuracy. Maybe it was not much high, but it was around 56, which was quite high, okay, in those days, okay, compared to the state of the approach. Then in till then, the problem of speech recognition, okay, and machine translation, okay. So all these things actually, many people at that time, people worked on speech recognition or machine translation. All of them were statistical in nature. Okay, they used statistical approaches. Okay, so when we talk about speech recognition, say 20 years back or 25 years back, so neural networks were not applied at that time. Only models, Markov models, we call them hidden Markov models, were applied. Okay, so HMM based systems, they were the state-of-the-art system at that time, which gave very good accuracy. Actually, you can see the literature and find that HMM based systems can do speech recognition with, say, 90% accuracy, more than 90%. Okay, so but actually, but when it comes to neural network, it could not match this accuracy of a then state-of-the-art system. So, but in 2010, Dahal et al., they built a speech recognition system based on neural networks, okay, and that could actually perform better than the state-of-the-art system, HMM-based system. Okay. Now you see, when some people overcome some problem of vanishing gradient and that exploding gradient, at that time, see, some people have applied with those algorithms, they have applied to speech recognition, and they found that now neural networks can perform better than HMM based system. Now you see that most of the current systems are all neural based. Okay, whether it is machine translation or you take it speech recognition, it's all based on neural networks, not on HMM based system. Okay, so that's the time when speech recognition was first succeeded using neural network. Then came along the GPUs, okay, the graphical processing units. This is actually a period when there is some improvement in technology in hardware. Okay, you might have learned about CUDA, okay, parallel processing, the GPUs, okay, which come under the category of single instructions, multiple stream, okay, SIMD approach. So this technology improved in this 2010, and people started applying those GPUs for training neurons. Okay, because you know the training itself takes a lot of time on a sequential processor, single processor. But if you have a GPU processor installed, then you can see that there's a considerable reduce in time. Okay, so people started using clusters, they started using clouds. Okay, they started using virtual machines. Okay, etc. And then it was a time that the researchers, they introduced the MNIST data set for digit recognition, handwritten digit recognition. Okay, so so the MNIST data set was introduced in 2010, okay, by Carson et al. Okay, and for the digit recognition, and they employed GPUs. The first superhuman visual pattern recognition achieved by same Carson et al. In traffic signal recognition, traffic sign recognition in 2011 by using GPUs. Then you should know that in ImageNet is a grand challenge that was introduced, visual recognition challenges from 2012 to 2016, in which this deep neural networks, concept of deep neural networks have become very, very famous and very, very popular among all other techniques. Now you see that you apply, you started applying deep neural networks to almost all applications, okay, all sorts of business. Okay, so this was a short actually thing, and now you see winning more visual recognition challenges. So the last point of what I was talking here, in 2012 to 2016, you see with different neural architectures came, something called AlexNet, JFNet, BGGNet, GoogleNet, MS ResNet. So you see the layers, number of layers each net has. See the number of layers, they have increased considerably, say from 8 layers, hidden layers, to 19 to 22 to 152. Say very big, say 1 to 152 is a very deep network, very deep network. But the problem actually with this thing is that this we cannot realize something in 2000 or before that, because if you use 152 layers of network, really at that time with those algorithms present at that time, people had the problem of vanishing gradient or exploding gradient. But because of the new techniques and algorithms that eliminated those vanishing and exploding gradients, it was possible to increase the number of neurons, okay, layers of neurons to almost 152. Again, I'll take a digression on Hubel and Wiesel experiment. Okay, so far what I have been discussing is about how multi-layer network was actually used. Multi-layer is you will have layers of neurons. Okay, say input layer from hidden layer 1, hidden layer 2, hidden layer 3, like that it goes. And at the last you have the output layer. But they wanted to have some change in the structure of the neuron itself. Actually, the network architecture itself had to change. And this change came about by going back to the Hubel and Wiesel experiment. This is again a Nobel Prize winning experiment in medicine. So where they used cats, okay, and what they inserted is they inserted some probes into the cat's brain, neurons, and they observed that when you look at a picture, okay, how your brain responds to that picture, how the neurons fire in the picture by looking into that picture. And they found that the brain consists of several neurons, sorry, not several, say many neurons, but all neurons do not respond in the same manner. Some neurons respond to different orientations in the image. For example, one set of neurons will respond to horizontal line. Another set of neurons will let's call it the sleeping line, sleeping position, horizontal line. Some neurons respond to the horizontal line, so vertical line, standing position. Some diagonal from left to right, some left to right. So different orientations of a line will enable different neurons to fire. So neurons are not agnostic of the images they are seeing, but they are specific to particular orientation. This was discovered in 1959 by Hubel and Wiesel, that they used cats, and they showed the cats pictures of lines, standing lines, sleeping lines, diagonal lines, etc. And they found that different sets of neurons fire for different inputs. So this was again a breakthrough in the experiment, saying that all neurons capture different features of the input image. That's what we call this. When you look at a complex scene, actually the complex scene is said to consist of several orientations, line segments in different orientations. So the entire brain being massively parallel neuron, so different sets of neurons, they extract different features, and they process different features, and the brain is able to assimilate all these features and bring about the complex imagery that what you are going to see. Okay, so this was the experiment that was done, and this gave birth to this new technique called the convolutional neural network. But again, you see that convolutional neural network is not again a very recent topic. Earlier topic in neocognitron, it was called by Fukushima et al. In 1980. It was actually called the neocognitron. Okay, so what you talk about convolutional neural network nowadays, it is actually the neocognitron that was done those days. And then in 1989, again, Lequin et al. They used this neocognitron to do handwritten digit recognition using backpropagation, and LeNet 5 on MNST data recently 1998. Okay, and so you see that even the convolutional neural network architecture is not new, but actually it is old based on the experiment involving cats. And again, further improvement came. People started getting better optimization algorithm like Nesterov algorithm 1983, Adagrad in 2011, RMS-Prop in 2012, Adam in 2015, Eve 2016 and beyond. Now we have 2008 and beyond Adam. So we have various types of optimization algorithm that we will see in detail as we go along. And as a result of that, this has become a commercially hit product. Okay, it has become commercially hit, and now people started applying almost to all fields of science, whether it is predicting how the galaxies, when two galaxies collide, how the galaxies behave, model. From that data onwards till to your stock exchange data, people have started applying neural networks, okay, for predicting various theories. Okay, and of course, so 2 more slides to go. I actually talk about inferencing from sequences. Again, here I told you that time is actually, we are not always, our input is not always a single input, okay, but our input is generally a sequence of inputs or series of inputs, where one input and other input, the next, so I call the adjacent inputs, they are correlated, okay, they are not independent, okay, they are correlated. In that case, it is called a sequence, okay. So for example, a Fibonacci sequence, or you can take an arithmetic progression, a geometric progression. So those are well organized progressions, but whereas if you talk about say rainfall prediction, or if you talk about time temperature or humidity, they are not such well formed sequences, but still we can infer knowledge from those sequences, okay. And so example of sequences are time series, speech, music, text, video, etc. And each unit of, that is each input, each unit of sequence interacts with the other units that follow it. It is essential to model or capture the interaction between the, or I will say capture the dependence between the inputs. That's very, very essential. So here you can see that, but what do you require for that? You require a recurrent network. You require the output to be given again as input to the network, okay. So it's called recurrent. That's why we call it RNN, recurrent neural network. Say for example, this is the original T and this is a corrupted form of T that is taken as a sequence, okay, sequence of data from taking. So of course, the recurrent able network should be able to eliminate this error and recognize that this is T, okay. So that depends upon that. And again, digression into history, that I'll show you that again, the RNNs are not new. They have been there since 1982, when the earlier RNNs were called Hopfield network. It was the content addressable memory systems for storing and retrieving patterns, okay. It's called content addressable memory. And Jordan network, say for example, this is a Hopfield Jordan network. So a Jordan network in 1986, the output state, so this is input, this is hidden, this is output. The output is again fed back to the hidden, okay, and this recurrent state is called the context. It's called the context. So here, in a sequence, the important thing is that the next output depends upon the previous output, okay, and that is called the context, okay. For example, in English grammar, if you say I speak, you speak, he speaks, then we say. So when I say I and you, say we say speak, but when I say he or she, he speaks. So it depends upon what person you are referring to. Is it the first person or third person, second person or third person? Okay, so that is called context. So that context is very important, and capturing that context, the Jordan network in 1986, that was done. In Elman network in 1990, actually the feedback was from the hidden state, not from the output state. If you take the feedback from the output state, it is called the Jordan network. If you take the feedback from the hidden state, it's called the Elman network. So it's all Jordan, Elman, all are actually networks that are recurrent in nature. Recurrent means the outputs are again taken as feedback and given along with the next. So the network input does not have only the input, but also takes the previous output. That's what you have to remember. So this is about the sequencing. Okay. Again, the problem was the same problem, again exploding and vanishing gradients problem was there, because when I talk about a sequence, you do not know how long that sequence will be. Say, for example, a sentence may be five words, or a sentence may even have say 50 words. So the length of the sequence may vary. Okay. So in that case, again, when the length of the sequence varied, what happened was, again the problem came up with the exploding gradient and vanishing gradient problem, and because of that, the RNNs were the half-wheel network and the Jordan network, they were not so much developed. But after the problem has been overcome by exploding and vanishing gradients, now people have started creating some LSTM cells. Okay, we call them long-term, short-term memory cells. Okay, to solve complex long-time log tests. For example, say if there's a dependency between two elements in a sequence which are separated in time by a long gap, then how to capture that long gap dependency? So I will give you an example later. So how to capture the dependencies that are not short range, but long range dependencies in a sentence or in a time series or whatever it is. So how to capture them? For that the people came up with LSTM cells. Okay, and in 97, and sequence to sequence learning was promoted by RNNs in 2014. And now people started not only using LSTM, but also they started using attention. Attention is again a mechanism that which part of the sentence, which part of the previous inputs you should look at. Say you need not look at all the inputs, all the previous inputs or outputs. You should look at only those things which are important to you. So how do you get that attention model? So there's again another type of learning called reinforcement learning. Using reinforcement learning, people developed attention models, and they have started using with RNNs and LSTMs. Okay, right. And in this process, the CNNs and RNNs have started beating humans in their own games. For example, if you take the Atari games, the Atari, Go, Poker, Defense of Ancients, they are actually games, computer games. So in all these games, neurons have been doing a very good job. Okay, all our recurrent neural network, or whether it is CNN, they have been doing a very good job. And I'll just sum up with the applications of the applications of modern deep learning. So one thing is language modeling. So what is language modeling? So language modeling is modeling the statistical behavior of languages using corpus, okay, or data sets of huge corpus. For example, how grammatically correct is a sentence? Okay, so you want to do that. So in natural language, it is not possible always to apply context-free grammars or context-sensitive grammars. So sometimes we may have to use statistical measures. So far statistical measures were used in addition to rule-based system, but with the advent of deep learning, people started modeling languages using deep learning models. Okay, so language modeling finds application in speech recognition, machine translation. If you improve my language modeling, your success is good in speech recognition and machine translation. Conversation modeling, say how question answering, how people talk. So when I ask a question, how the response will be, whether so here you should remember the Turing test proposed by Alan Turing in 1952 itself. He said you ask a question to two persons, A and B, where A and B, one is a person, other can be a computer. You do not know who is a computer, who is a person, and you are asking a series of questions to both A and B. You get answer. And if you are able to distinguish that A is a computer or B is a computer, then the computer has defeated. But if the interrogator, the person who is asking the question, is confused and he's not able to decide which answer is coming from human and which answer is coming from computer, in that case, Alan Turing said that computer has become really intelligent. That's called the Turing test. So now you see that this Turing test, the computers are now beating the Turing test, okay, because now you have all these soft bots and all this question answering system, which are even commercially there. It answers to questions from the user, and you do not know whom you're talking to, whether you're talking to an operator or you're talking to a computer, okay. And then when it comes to visual image processing, then you have object recognition, object detection, visual tracking, looking at an image, telling what that image is all about, describing an image or describing a video, or we call it image and video captioning, or you look at an image and answer some questions from that image. Say, for example, you look at an image and say how many cars are there or how many buses there, so something like that. You give an input and visual image, give an input and you ask questions. The questions will answer, the computer will answer, describe based what you're asking about the image. Then video summarization. So up to this point there has been a lot of improvement, and now computers are able to generate, not only recognize or detect, but they are also generate. Your computer can generate music, okay. You say, just say a folk music will be generated, okay. And I'm not talking about folk music will be replayed, no, not replaying, it is actually generating music. A computer can create an authentic photo actually of a person who is not alive. So it's not a born or a dead. Actually, it can, based on its corpus, a computer can create an image of a person who actually never born. Okay, it will be an authentic photo. Okay, so you can generate authentic photos, and you can make your black and white movies into a color movies. Okay, like that. So many applications are there which apply deep learning. Okay. So we'll go to, as we go along this course, I'll be discussing one by one, but again will not be able to discuss much because this is a very short time, and actually I'll try to my best to describe or to discuss different issues in whatever things we have seen today, okay. But actually if you want to go deep really into it, then you may require to go take at least, say, you may have to spend quite a long time in CNN and RNN, okay, and sequence based models, okay. So it is really a vast field, okay. So but the good news is that you have a lot of hardware that are available, you have cloud facility available, you have libraries available. You have many of the works have been done already, so you need not create anything from scratch. You have to use the facilities that are available, okay, and improve upon the things, okay. So this is how actually we have to go about. And the last two topics what I told about generating authentic photos and generating raw audio. So they are called generative models, okay. So they are open in research. Okay, we call them generative models. Okay, okay. So this comes to the end, the first session today. Okay, so just I gave you about the history of neural networks and how it developed. Okay, and say how it can be applied to different applications. Okay. So thank you for joining this session. I thank you wholeheartedly, and I'll take queries if any.
Participants, if you have any queries, you can raise now. If you have any queries, you can raise now, or else you can use your WhatsApp media to raise the questions.
Yep. Yeah. This second. Okay. Yeah. So I take some questions. So one is the difference between RNN and the CNN. Okay. So the difference is that CNN, you give an input which is one-time input. Actually, you give an image. Okay. If you give an image and ask what is that image, whether it is it's a car or it's a bus or it's a cat or a dog, you classify. Okay. In that case, your input is a one-time input, and your output is actually a classification. The next input you give will not be depending upon the previous input. So CNN is convolutional neural network. Okay, but RNN is actually a recurrence neural network in which your inputs will not be a single input, but it will be a spread over a period of time. Okay, so it will be a sequence like frames in a movie. Okay, so I will be giving frames one by one. So in that case, so CNN can be a part of RNN. So I'll just tell you that when we talk about this, when you're talking about video, describing a video, in that case, your inputs will be frames of video. So it will be, your input will be a CNN and your output will be a RNN. Okay. So I think you get it. So we'll see in great detail about them. Okay. So one question is, somebody has asked, what is F? So I'm not sure what is that F you're talking about. Balasubramaniam.
Okay, thank you, sir. Thank you, participants. If you have any questions, you can also put it in your WhatsApp group. We will try to answer your questions. So, thank you, sir. Thank you for the wonderful eye-opening session on this deep learning. I'm sure the participants really enjoyed, and they're actually looking forward for your tomorrow's session. So, participants, I have shared the attendance link in the chat window. Request you all to immediately record your attendance. The link will be enabled for the next 5 minutes. The link will be closed by 12:45. So I request you all to record your attendance before that. So in the meantime, you can also use our WhatsApp group to raise your questions. If you have any things to convey or anything to ask, you can also use our WhatsApp group. So I will meet you tomorrow at 10:30. So tomorrow's session will begin at 10:30 and it will end at 11:30. So thank you all. Thank you.